Damping. Well, what's damping? Damping is basically a resistance to motion. Okay? And that resistance, we're going to just be talking about viscous damping, which is a resistance to motion, okay, and it's proportional to the velocity of that motion. If the system is not moving, there's no damping force. Okay? So like you pull back a spring and a damper, and you hold it there, okay, the damper does nothing. Okay, but the spring force is trying to return it. You let go, obviously you start getting motion, okay? So the spring is going to force it back, but the damper is always opposing that motion proportional to how fast the thing's going. Okay, that's what a damper does. A damper in your car, shock absorber, is exactly the same thing. If you had no shock absorber in your car and you hit a bump, the car would oscillate forever, okay? It would just keep going up and down because you've excited it, okay? Whereas the damper will take out that energy, okay, by using, like I said, and that energy that is taken out is proportional to how fast the thing is moving, okay? Viscous damping is what it's called. So the force opposing the motion, this is really important. The same with springs. Spring force and damping force will always oppose motion, okay? It will be opposite to the way the thing wants to move, okay? So the damping force is C, which is our damping constant, okay? And that's a characteristic of the damper, times by the relative velocity of x and y, okay? X dot minus y dot. So that's, it could be shown as a real damper. Often this bit up here, you'll have some sort of orifice through the piston, okay? So fluid can go from one side to the other, okay? And we all know that orifices, back in level 1 fluids, that will cause some sort of that's a restriction, and that restriction will control how quickly that damper can move, how quickly that piston can move through the fluid, okay, which is obviously causing you damping. This is a schematic of how dampers are drawn, okay, and so you'll see that quite frequently. So we've got a mass spring damper system, MSD system. You'll come across this loads and loads and loads of times because this is now a real system, okay? We've got a damper and a spring. And so if I started that oscillating, what do you think will happen after a certain amount of time? It's going to stop, yeah? And the reason it stops is that we're taking out energy using the damper, okay? And so as time goes to infinity with this system, what happens to the amplitude? It goes to 0, okay? So if we start looking at using second law, mass times acceleration equals the sum of the forces. Well, I've got two forces. They're both opposing. I've got my damping force, Cx dot, and I've got my spring force, Kx. Okay? They're both opposing, hence the minus signs. And I can move them both to one side and end up with this equation, which again is one of the fundamental equations in all of physics. And you'll see this in the first lecture of the control series, okay? Because it's often talking about mass spring damper systems. Mx double dot plus Cx dot plus Kx equals 0. And you'll see that again and again in this course as well. Okay? Often we'll have an F at the other end, but instead of a 0, but that's by the by. And we're going to set some shorthand notations, okay? Omega naught squared is K upon M. That we saw before. But this new one, gamma, okay, is C upon M. So if I take that equation, that one there, and if I divide both sides by m, I end up with C upon m and K upon m. And obviously K upon m is omega naught squared, and C upon m we've just defined as gamma. Oops, computer. So the equation of motion could be written like that. Now the challenge is to find the solution of x of t. X is a function of time. And we can make the prediction that the system will oscillate at a frequency at or less than the natural frequency. Now if you think about it, if damping is low, really low, okay, and you let the system oscillate, it's going to go backwards and forwards, and the frequency of that oscillation is going to be omega naught, okay, because there's no damping. But as you increase the damping will slow the motion down, yeah, because it's responsible for taking energy out of the system, and that the amount of force that's being applied is proportional to the velocity. So it's going to slow it down, okay? And so what do you think happens to the frequency? Okay, yeah, it decreases, it goes down. The frequency will slow down, okay? So we can make a prediction that omega, the frequency at which the system is going to oscillate, is going to be at or less than omega naught, okay, with a damper. And this is an example where the complex plane will help solving this problem. We're actually going to use it a couple of places. So, the oscillator will die out. So we're going to move to the complex plane. We're going to replace x with a complex number, okay? And I've called that complex number z, okay? So we've just stuck z in where we had x, okay? And the trial function now, we know that z is a complex number, so we're going to try the fact that it's going to oscillate, okay? Now I've got p, t and alpha in here. Let's not worry too much about it, but remember the p, with that form of that equation, p smells a bit like a frequency, yeah? It's, we had j omega t plus some phase angle. So alpha is a bit like a phase angle, p is a bit like a frequency, okay? They're not just at the moment, but let's just think about that. We're going to try that as a trial function because we know the system is going to oscillate, but we don't know at what frequency, we don't know where it's going to start in terms of the equation. So that we can apply this as a trial function. And so we take derivatives. So obviously the first derivative, you get a jp coming out. Okay, j times p times t. The alpha, obviously the derivative of a constant is 0, so that disappears. You take the second derivative, so that's jpz because that's z, so you end up with jpz. Second derivative, obviously you get another jp coming out. J squared is minus 1, hence the minus sign, and p squared is obviously p squared. And so the second derivative is minus p squared times by z. Let's stick that back in the equation. So there we are. So we've stuck in, for z double dot, we've stuck in minus p squared. Okay. For z dot, we stick in jp times by gamma, because obviously you've got gamma up there. And here we've got omega naught squared times by z. Okay, so you've got that in there. That's what we had before. Now the only way this equation can be solved is if we make p a complex number. Okay, so we're using it again. P is a complex number. If you think about this equation up here, okay, the only way that we could solve this equation is this: either z is 0, or z is our oscillation. That can't be 0, okay? So that can't be 0. Therefore, this lot must be 0. And if you've got a complex number, which that term is, okay, we've got two real bits and a complex bit. For a complex number to be 0, the real bit needs to be 0, and the complex bit needs to be 0. And the thing is, p can't be 0 because that's a frequency. Like I said, it smelled like a frequency. Omega naught can't be 0 because that's our frequency of oscillation, and gamma can't be 0 because that's no gamma. I mean, damping is not there. Damping is there. Okay, so that term can't be 0. Therefore, we've got a solution here that we can't seem to solve. But if you make p a complex number, we can solve it. And so that's what we've done. P equals n plus js. Again, n and s, they're just terms we've been using. They'll disappear in a minute. So we make the substitution in there. So obviously p squared is n squared plus minus s squared plus 2jns, okay? So we can stick that in for p squared, and obviously the minus sign in front of the s term, this one, is because j squared is minus 1. Okay? So we can stick that into where p squared is, and obviously where you can stick in for p, we can stick in n plus js. So end up with this equation on the bottom. Now look at what happens, okay? We've got a real bit, and a real bit, and a real bit. That can be equal to 0. And this odd bit as well, can be also equal to 0, depending on what certain things are. So if we move through, real parts must sum to 0, imaginary parts must sum to 0. So if you take the real bits, okay, s must be equal, sorry, the imaginary bits, s must be equal to gamma minus 2, gamma upon 2. Take this equation, set it equal to 0, you get a value for s. And if you do the same thing for this bit, obviously here we can substitute in for s with gamma upon 2, so that's why we've got gamma squared upon 4, gamma squared upon 2 in there. N squared must be omega naught squared minus gamma squared upon 4. So we've got two terms which combine to make p. And so if we remember we had z equals a j p, pt plus alpha. Well, we stick in for p, nt plus j, n plus js, and so you get nt plus jst. Obviously, with an exponential, you can separate it out. So we've got a e to the j times jst, and then e to the j nt plus alpha. This, like I said, looks like that. The real part of that is an oscillation, isn't it? Yeah? Where this turns into minus gamma upon 2 times by t. Now that, notice we've got the multiplication of two imaginary parts. Okay? One of them is an oscillation, this one here. Yeah, that looks like an oscillation. We all agree? That's what we just covered in compensation. This one, what's going to happen as t goes up? T is 0, what's the e to the 0? 1, okay? As t goes up, what happens to that term? It goes down. There's a minus sign here. It's a decaying exponential, okay? If I was to draw e to the minus x, here's my x and y. There's 1. E to the minus x, it passes through 1 with a slope of 1, okay? A slope of minus 1 and goes down and decays to 0. Okay, so e to the minus anything will be a decaying exponential. That's the whole, that's another reason why this is called e. It's an exponential, okay? Decaying exponential. And so we've got two exponentials multiplied together. One of them we know is an oscillation because we just talked about complex notation. E to the j anything will be an oscillation. The real parts of that will be an oscillation. Whereas e to the minus some constant or some something with respect to time will decay as time goes up. Okay, and so if we let's come out of this. So like I said, e to the minus gamma upon 2 times by t is a decaying exponential, and e times j times something we know as an oscillation with a frequency of n in this case. Now n is a frequency and it's known as the damped natural frequency. Okay? And that is a frequency at which the damped system will oscillate. And that frequency depends upon your damping in the system. Okay? It's dependent upon gamma, which is C upon M. And obviously C is your damping. And so if we stick in, we had up there, we've got nt plus alpha. Okay, we've got gamma upon 2. So you stick in n equals omega d, you get an omega d in there. Okay, and so here we've got our equation for z. The real part of z, so obviously the e j omega t stuff moves to cosine j omega t. And so you end up with our solution. A, e to the gamma upon 2 times by t, times by our oscillation of frequency omega d. Okay, that's an amplitude. There's no issue with that. This bit is our oscillation. Okay, and the frequency of oscillation is omega d, a damped natural frequency. This bit here is the new bit, and that's causing it to decay, the amplitude of decay, to 0 as time goes up. So you can see quite clearly that, x of 0, the starting off time, you're going to end up with a times by 1, because that's 0, so that term becomes 1, a cosine omega t. So it's going to start oscillating. You put it back, a mass spring damper system, you put it back, let it go, it's going to start oscillating. Okay? But obviously as t goes up, that oscillation is going to reduce in amplitude with respect to this term. And as t goes to infinity, so eventually, okay, that term is going to be 0, so the oscillation stops. Okay, that's the solution for a damped system, mass spring damper system. Okay. Now we'll cover when we come to the alternative terms section, alternative terms for gamma and in fact gamma. Yeah, you'll see that change. Okay, but let's not worry too much about that right now. But you can see quite clearly the equation's made up of an amplitude, okay, which is what you set it off as, an oscillation of frequency omega d. Let's not worry too much about what's going on here. That depends upon initial conditions. And the fact that this term will start off and then decay off away, okay? And that decay will depend upon this term, the gamma term, which is which is related to how much damping you've got. Okay, low damping, it's going to decay really, take a long time. Really high damping, you could end up with the oscillating or not oscillating at all. If this is critical damping, you put it back, let it go, the thing's going to move back and stop at 0. That's critical damping. Okay, if it's most systems are slightly underdamped, so it will overshoot and then come back. But depending on how much damping, depends on how many times it overshoots and where it stops. Okay. And again, you'll come across this in control. Most systems are underdamped, so they'll overshoot and come back and then settle. Okay. So if we plot that, we end up with this situation. Okay. So like I said, here's my equilibrium position. I pull the thing back, or I lift it up, or whatever, by a certain amplitude, and I let go. And depending on damping, we end up with an oscillation that decays with respect to time over and over and over. Okay. Here I've listed x1 as my amplitude A, x2 is the second peak, x3 is the third peak, and x4 is the fourth peak, and so on. And there's a relationship known as the logarithmic decrement that dictates how quickly the system will decay in terms of time. Again, that is related to how much damping you've got. It's in your notes, but I've not got it on a slide. Okay, so if you look on page 21, section 2.3.2 is about the logarithmic decrement and talks about the relationship between xi plus n and xi. Okay, and that's again related to E. There's another example of where E comes up, showing its significance, and you can see that that's the decay that's happening. So, overdamped system. So like I said, if you remember, we had where is it? N is omega naught squared minus gamma squared upon 4. Obviously, you take the square root of that, you end up with omega naught minus gamma upon 2. And N we saw was equal to omega d. Okay, so there's omega d squared. If gamma squared upon 4 is greater than omega naught squared, we can write down an equation for N. Now, it just so happens, if you substitute that back into the equation of Z and turn the crank, taking the real part, you get this, which is your solution in the case of an overdamped system. And you can see that that's two decaying exponentials added together, and so you end up with a system that does this, or it does the curve A. Okay, you take a system, if it's got overdamping, you pull it back, you let it go, and the thing will just will start off slowly, will slowly decrease, and then end up settling at 0. Okay. If you give it some initial velocity, so you pull it back and then you give it a push, okay, you get this equation of B. So you've got an overshoot, okay, but that overshoot is only because you gave it a velocity to start with. There's nothing to do with the fact that it's overdamped. And again, it just settles back to 0. An overdamped system will never ever oscillate. Okay. Sometimes you want that, often you don't. You want a little bit of oscillation. Okay, not much, but a little bit. And basically, it takes a very long time for it to settle. Okay, depending on how much damping you've got, it'll take forever. Whatever. So. Critical damping, that's the case where omega naught equals gamma upon 2. Okay, natural frequency equal to each other. Okay, and what happens with critical damping is you end up with, again, just a term times by a decaying exponential. So again, it's not going to oscillate. There's no cosine term in here. Okay, and oops. So you're going to get something that looks a little bit like A, but it's going to be the quickest way to get to 0 without overshooting. That's critical damping, basically. I haven't got a picture of what it looks like. And then, obviously, the other case, which we looked at already, is where omega is greater than gamma upon 2. And you get an underdamped system. Okay, and that, like I said, that's where you get the cosine term coming in. So we've got three solutions. We've got this solution, okay, which is damped oscillation, underdamped oscillation, and that gives you that result. The overdamped case, which I've given you there, you don't need to worry too much about remembering that equation because we won't use it that much at all, if at all. That's the overdamped case. And like I said, the critical damping looks a bit like the overdamped case, but it's the quickest way of getting to 0 without overshooting. Okay, that's all that matters. Right. So, force damped oscillation. This is where the fun begins. So this time we've got the same thing, a mass spring damper system. Obviously I've got a displacement of x, okay, and I've got a force that's being applied, F of t. Okay, mass spring damper system, I've moved it back x, but there's a force that's being applied as well, F of t. And then again, we're going to apply a sinusoidal force. We'll talk a little bit more about these different forces in chapter 3, but let's take a sinusoidal force. So again, Newton's second law, mass times acceleration is the sum of all the forces. So we've got the spring force minus kx, we've got the damping force minus cx dot, and we've got our force that's being applied, F naught cosine omega t. Now again, omega is not the natural frequency, it's not the damped natural frequency, it is the driving frequency. It's the frequency I'm giving to the system. F naught is the amplitude of that frequency. So we can make our substitutions, C upon m and k upon m, so we end up with this, and we're moving to the complex plane again. So replacing x with z, complex number. And because we're using a complex number, we can try a trial function. We know that the system's going to oscillate. Notice I've changed the cosine omega t to ej omega t, because we know that that's an oscillation. Okay, we're going to try a trial function. And we're going to predict that the frequency of that trial function will be omega, because it's going to end up going at that frequency anyway. Okay, we've got a phase in here, which is delta. We'll worry about that in a minute. And we've got a certain amplitude. We don't know what that is yet. So we'll stick that in for z and see what happens. So we stick that in for z. We end up with a minus omega squared plus j, gamma j omega plus omega naught squared. Okay, e j omega t minus delta, and that's f naught upon m e j omega t. Okay, because remember we took this equation, this one here, and divide by m, you get f naught upon m over here. Okay, so we make that substitution. We move into now the e j omega t terms, they'll cancel out. Okay, so on one side we've got e j omega t, because remember what you've got when you've got a sum up here, you've got e j omega t times by e to the minus delta. Okay, it's the same thing. And so ej omega t and ej omega t, they disappear, okay? And so we end up with this equation, and this was e to the j times by minus delta. Well, obviously, if you divide by it, it becomes e to the j delta, which is why it's over here, okay? Still in the complex plane, we could rewrite the right-hand side over here. So all I've done is I've taken that term. We know that's a complex number, so that's in there. Yeah? Does that make sense? And the real and complex parts must be equated to each other. Okay, so the real bits must be equal to f naught upon m times by cosine delta, and the complex parts must be equal to sine delta. And so we can do that. Okay, so you end up with this equation. So there's our real bits. We've got a minus omega squared and a plus omega naught squared times by the amplitude a must equal f naught upon m times by cosine of delta. And then the complex bit in this equation, we've got gamma j omega, okay, times by a must equal f naught upon m times by j sine delta. Or the j's disappear. We end up with that, the imaginary bit, with that bit, which is an imaginary bit. They must be equated. Remember, this is where we had the problem where, back in the free oscillation, there was no force, so this bit on this side was 0, and obviously that couldn't be 0. Okay, so that would mean the amplitude is 0 and the frequency was 0, and the gamma was 0, which is, just doesn't make sense. Two equations, two unknowns. Okay, a and delta are the things we don't know, and you can do the maths. I won't bore you with the arithmetic, but that's what it comes out. A comes out to be that, and delta comes out to be that. Okay, so we end up with two equations. Now, they're in your notes. If you look on page 24, you can see those two equations. And obviously, you can return to the real world. We know what A is, and we know what delta is. Okay, they're defined there. So that is the equation for a forced oscillation system, okay, with damping. And again, that A cosine omega t minus delta, that's almost equivalent 100% with the case where you've got no damping, okay? Again, the system will oscillate at the frequency at which you're driving it, okay? The system will oscillate, like I said, it doesn't matter what it wants to do, you're driving it at a certain frequency. If you're strong enough, it will go at that frequency, okay? Now, again, A is not adjustable. It's dependent upon your system and the force that's being applied, as is the phase, okay? So again, like the forced system with the free oscillation, it doesn't matter what happens to start with. A will be determined entirely by your system. So you've got F, which is your frequency, you've got your mass, which is obviously the mass of damping, the natural frequency system, which is related to the mass and the stiffness of the spring, that's the frequency you're driving it, so you know it, and gamma, which is C upon M, and you know what C is because, again, that's a characteristic of the system. A is completely reliant on the system, okay? And the same thing with delta, okay? Delta's just got omegas and gammas in, and you know all those things. They're related to the system and the force at which you're applying to the system. So they are no longer adjustable, okay? So with the free oscillation, basically free oscillation, A and your phase, okay, will be dependent upon initial conditions. What happens when you start the oscillation off? The same with damping, with damped and with undamped, okay? You will define those based on initial conditions. If there is a forcing function in the system, as if you're forcing it with a frequency, okay, frequency that you decide, and with an amplitude you decide, the system will therefore respond in a way that's completely defined by the characteristics of the system and the force you're giving it. Okay, it's no longer reliant on initial conditions. It doesn't matter what the system is doing when time is zero, okay? You will give it a forcing function and the system will respond, and eventually when all the transients die away, you'll end up with this situation where you've got an oscillation with a certain amplitude dependent upon the system and a certain phase dependent upon the system. Constants A and delta are not adjustable anymore, and they're defined by the characteristics of the system and the characteristics of the applied force. Now we can look at what happens. There's our equation for A. Okay. Let's look at what happens when we have different values of omega. This is the driving frequency, so we can choose that, whatever we want it to be. Omega naught is set by whatever we've got our system set at, in terms of the mass and the stiffness of the spring. Okay. But omega we can choose. Omega without the subset, we can choose whatever we want that to be. We can drive the system at a very low frequency, or we can drive it with a very high frequency, or we can try and drive it around the natural frequency and see what happens. And what we can do is we can stick in different values for omega and then plot the results. And we'll see in this minute the plot, but basically, as omega goes to 0, we end up with F0 upon K. That makes sense. That's a static displacement. If you're not oscillating the system, you pull it back, the force with a force, okay? The force is just going to be being opposed by the spring, yeah? And the spring force is K times the displacement, okay? A is the displacement, time multiply that, K, you get a force, okay? So that's static displacement, that doesn't change. And that's what happens if you stick an omega naught into this equation, omega equals naught into this equation, that term disappears completely, that term disappears, we end up with F naught upon M times by the square root of omega squared, which is omega naught. And obviously if you do the maths, you end up, the M's cancel, you end up with F naught divided by K. Okay, that's what happens there. So like I said, if you look at the equation, you've got F naught upon N. The omega squared cancels and the omega gamma, these two terms disappear because they're equal to 0. So you end up with the square root of omega naught squared, which is omega naught, 1 upon omega, so that's squared times squared, so that will end up being just squared there, okay. And obviously that's root K upon M. That is M, K upon M, okay, but obviously it's upside down, so it's M upon K, okay, and obviously the M's cancel, you end up with F naught upon K. That makes sense. And like I said, that's called static displacement. What about delta? Well, delta is there. If we set omega to be 0, okay, then obviously it's a inverse tangent of 0. Okay? An inverse tangent of 0 is also 0. Okay? Because tangent at 0, tangent is also 0. Okay? So if omega naught, delta is 0. Now what about if we're driving it at the resonant frequency? Well, if omega and omega is almost equal to omega 0, if we go back to our equation for A, if those two terms are equal to each other, okay, then obviously that term becomes 0, yeah, and that term becomes omega naught, because that's what we're driving at that frequency, okay. So you can put the values in, you end up with this term, f naught upon k times by a constant that's dependent upon the system, okay. Omega naught is root k upon m, and gamma is c upon m, okay, so we can basically, you've got, if you remember when we're with a undamped system, and the A went to infinity, didn't it? Okay. Well, you can see that in this case, with damping, it doesn't go to infinity. It goes up by a certain amount, and that value we call Q, which is the quality of oscillation. Now, we call that quality, basically, if the system's good at oscillating, so the damping is low, then it's got a good quality of oscillation. You can see that makes sense. Okay. If damping is low, then Q is going to be high. And if damping is high, it's on the denominator, then Q will be low. It's a poor quality oscillator. So think of that Q as being quality of oscillation. And so you can say that the amplitude, when you've got omega approaching your natural frequency, is going to be some factor multiplied by your static displacement. Okay, some factor multiplied by the static displacement, and that factor Q is dependent upon your system. And then, in the case where the driving frequency approaches infinity, our A equation will end up being upon infinity, f naught divided by m divided by infinity, and obviously that's approaching 0. So again, the same situation happens. You start off when omega is very low at your static displacement, and then as omega goes to infinity, okay, your displacement goes down to 0. Okay, as your frequency gets higher and higher and higher, the amplitude of oscillation will reduce. But around the natural frequency, it's going to increase by a certain value, and that value, instead of it going to infinity like it did with the undamped case, because there's damping, it doesn't go to infinity, it goes to a peak. And that peak will depend upon the damping in the system. It's less obvious what happens to delta in these two cases, and let's just say that this is what happens. At omega, so delta is the phase. At omega equals omega naught, okay, the system will respond 90 degrees out of phase with what the force you're giving it, okay? So if I'm applying a force this way, it's going to wait 90 degrees of the cycle, and then it will respond as well. So you get this sort of situation like this, okay? So the system will be delayed in its response. As omega goes up and keeps going up, you end up getting the situation where you're 180 degrees out of phase, okay? Pi radians is 180 degrees, where if you're forcing like this way, it's actually moving this way, so you get this sort of situation. So you start off, very low frequency, it does this, okay? And slowly, as you increase the frequency, okay, you get a delay in the response, okay? And then as you go further and further and further, you get it being completely out of phase with each other, okay? You see that in control as well, when you talk about frequency domain stuff. So this is what it looks like. There's A, okay? Start off at omega equals 0, okay? You've got f naught upon k, static displacement. As you increase your frequency to omega naught, okay, the amplitude is going to go up. And it depends on your damping. With very high damping, it doesn't go up by much. With very low damping, it goes up quite a lot. And like I said, with zero damping, it goes up to infinity, doesn't it? Yeah? So it goes up to infinity. So with f naught upon k, it goes up to a certain point, and then will fall back down to 0 as you increase your frequency. And your delta, if we plotted the same thing with delta, at 0 frequency, okay, there's no phase. It's going to respond in the same way that you're applying the force. Okay, as you increase your frequency to this point, you're going to be a bit behind, okay? and then as you go beyond it, it becomes more and more like a completely opposite. And again, the speed with which it goes from 0 to 180 out of phase is dependent upon your damping. If your damping is very high, very high, which is this line, it takes a long time. If your damping is very low, then obviously the speed changes quite quickly. And obviously 0 damping comes along here, you hit the natural frequency, and it shoots up and goes negative. That's what we had in the 0 damping case. Now you'll notice, if we look at this thing, the peak of the amplitude, so this bit here, there, and there, notice that it happens slightly before your natural frequency. And that depends upon the damping, And then the less damping you have, the more likely it is actually at the natural frequency. But that peak doesn't actually occur at the natural frequency. And there are equations that will help you define that. So the frequency at which the maximum does occur, which is here, A max, is equal to this. And you can see that that depends upon Q. Q is omega naught upon gamma, so Q, the quality of oscillation. So you've got an equation there that's dependent upon the natural frequency of the system and the damping that's in there. If damping is very low, then Q is big, and you end up with the square root of 1. 1 over something that's huge is 0. So you end up with the bit being at the natural frequency. If Q is very low, so damping is high, then obviously this number comes into play and it reduces the value of omega naught, or reduces this number becomes a number that's less than 1 times by omega naught. The maximum amplitude actually is slightly different to what it is when you've got, obviously what we've done here is we've stuck in our omega into that frequency, and that's what the end of what you're getting there. So by way of example, if Q is 5, so very underdamped, equivalent to a damping ratio, we'll cover damping ratio next week, but damping ratio 0.1, then omega max is 0.99, so it's 0.99% of omega naught, so it's 1% lower, and A max is F naught upon K, so it's 5.03, so it's only 0.6% higher than Q. So it doesn't actually make that much difference with a very underdamped system, whether you take these equations or those equations, for the frequency. But with obviously as damping increases, it will make a difference. Right, we'll save that for next week. Thank you very much.